I wanted to go over how to do some of the initial rate calculations with the examples on the rate note. In example number 1, they tell you that you have 144 grams of carbon dioxide gas and it's being produced every minute during a chemical reaction. They want you to report the rate in terms of moles per second. So this is what they need us to get, rate in moles per second. Per means over, right? Per second. So we know that if we're given mass, we can convert that into moles by using mass over molar mass. So I take the mass, I look up the molar mass of carbon dioxide, and I figure out how many moles that's equivalent to. Because they want the rate reported in seconds, they tell me that every minute, so I have to convert minutes to seconds. So we know that there's 60 seconds in every minute. And if we take a look at the entire equation written like this, we just put everything in. Remember our sig fig, when I take a look back in the original question, there's 3 sig fig. So I'm going to keep my final answer. I can leave it like this, moles per second, but it's more appropriate to report it as scientific notation. And remember that our units can be written as just a numerator only by taking your denominator and making that seconds to the -1. So moles per second or moles times second to the -1. And looking at the second example, what we want to make note of is we have ethane, which you know the formula of, and they're telling you that 11.2 liters of ethane gas are consumed, meaning used up, in a natural gas furnace every minute. Calculate the rate of formation of carbon dioxide gas in grams per second. So we can assume at this point, because it's being burned, this is a combustion reaction, and they don't specify whether or not this is incomplete or complete, so you just assume complete combustion. So at this point in time, what you want to do is you want to write out a balanced equation, and I want to know for every 1 mole of ethane gas, how many moles of carbon dioxide do I have? So I notice that this is a 1-to-2 ratio. What they're asking me to find is how many grams per second of carbon dioxide am I making? So instead of in the above equation where it was moles per second, they want it in grams per second. So step 1, balanced equation. Step 2, what I do is I have to remember some of my laws from grade 11, and my gas law in grade 11 told me that for any mole of gas at STP, meaning standard temperature, standard pressure, 1 mole is equal to 22.4 liters. So if I'm at STP, I can use this relationship. 1 mole of any gas is equal to 22.4 liters, but what I've got is 11.2 liters. So how many moles is that equal to? So that's equal to half a mole of ethane. Then what I do is I want to figure out, well, how many moles of carbon dioxide are being produced? When you look at the ratio, it's a 1-to-2 ratio. So here's some stoichiometry that's happening. So for every 1 mole of this, you get 2 moles of carbon dioxide. I only have half of a mole, so that is equivalent to 1 mole of carbon dioxide being formed. Because I now know moles of carbon dioxide, I want to convert that back into mass. And when I convert that back into mass, then I have 44.01 grams. So I did moles times molar mass. Then what I want to do is I want to convert this information into a rate, grams per second. So here we go, grams per second. And because they said it's for every minute, I converted my minutes into seconds again, and I get an answer of 0.734 grams per second. In the next equation, what they want us to do is to use this graph in order to determine the average rate of a reaction. So average rate means over a given period of time. So here they're asking you to figure out from 0 to 50 seconds. So if I was to take a look at the reactant line, I noticed that you have some reactant at time 0. There's the concentration on the y-axis and time on the x-axis. So you have some, and over time that reactant gets used up as the reaction proceeds. And when we come to a plateau, that means that the reaction has come to a stop. And for a product, we don't have any product at time 0 until those collisions start to happen and you start to get the reactants converting into products, right? bonds breaking, bonds reforming, and then we come to a stop. So if I was to take a look at 50 seconds for reactant, we have a change in concentration going from 1 to 0.3. But remember, change in concentration is final minus initial over 50 seconds. And you notice that I get a negative rate value. Now that negative isn't negative on the number scale. That negative indicates that the reactant is being used up. Just like in the enthalpy unit, the negative means it's exothermic. In the rate unit, it just means that a reactant is being consumed. This capital M is the same thing as saying moles per liter. Remember, it's the short form version of writing that. If we were to take a look at the product, because these two lines are pretty much just mirror images of one another, we would expect that the rate at which a product is being formed would be the same. And when I take a look at that, I take a look at where 50 seconds is, I go over, extrapolate that data, and I get 0.7 minus 0 over 50 seconds, and you get a positive rate value, which means that products are being made. The initial rate of the reaction would be 0 because at time 0, nothing has happened yet. So we would say 0. Hope that helps, and all the best.